colleagues, guests, friends of UKZN, good afternoon. On behalf of the Vice Chancellor and Principal, Professor Nana Poku, it gives me great pleasure to welcome you to the inaugural lecture of Professor Oluwatosin Mewomo. The Vice Chancellor conveys his congratulations and best wishes to Professor Oluwatosin Mewomo. Inaugural lectures form part of the university's public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers of our university. Inaugural lectures present an opportunity for showcasing exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic's career, providing official recognition of their promotion or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution to their field to academic peers, students, and research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievements with his or her family, friends, mentors, and colleagues. I would like to also acknowledge the following guests as I welcome you. Members of the executive management of the University of KwaZulu-Natal, members of Senate, our inaugurant this afternoon, Professor Mewomo, family and friends of Professor Mewomo, academics and professional staff, guests from the African continent and abroad. I'm very, very pleased to see that we've got guests that come from many institutional memory tertiary institutions in the context of this man's exciting day as a professor. This is institutional memory in the sense that these are the institutions of education that he has worked with. Some of them contributed to his education. I see research institutes, governments, collaborators, and partners from all over the world. I would like to also welcome his students and other students who are joining us today, UKZN alumni and distinguished guests. It is now my pleasure to introduce our Dean and Head of School, Professor Delia North, who will now formally introduce the inaugurant, Professor Oluwatosin Mewomo.
Thank you very much, Professor Modi. Good afternoon, staff, students, and many academic visitors. It's my absolute pleasure, privilege, and honor to introduce Professor Oluwatosin Mewomo, who will be delivering the inaugural lecture this afternoon, titled Notions of Amenability in Banach, Algebras, and Fixed Point Theory, a Career in Two Paths. However, before I hand you over to Professor Mewomo, I would like to tell you a little bit more about this remarkable mathematician at UKZN. Professor Mewomo obtained his PhD in mathematics from Federal University of Agriculture, Abeokuta, Nigeria, in 2007, where he was an academic staff member for 13 years before joining UKZN in 2015, initially as a senior lecturer, but has risen through the ranks, and we are here today to celebrate his 2020 appointment as a full professor in mathematics in the School of Mathematics, Statistics, and Computer Science at UKZN. Professor Mewomo's research area is functional analysis, in particular, Banach algebras, fixed point theory, and applications to nonlinear and optimization problems. He has successfully completed the supervision of 14 doctoral and 22 master students, mentored 4 postdoctoral fellows, and published over 180 research articles in Scopus and ISI index journals. He is currently supervising 5 PhD students and has a Google Scholar citation of 2,449, a H index of 30, and I index of 72. Professor Mewomo has been an NRF C2 rated scientist since 2019 and has been one of the top 30 researchers across the university at UKZN for the past 3 consecutive years, most recently coming in at number 2 at this institution in terms of research output. So I think you will agree, it's quite an amazing feat. Professor Mewomo has further examined several master's and PhD theses, both within and outside the continent of Africa. He's a reviewer of several prestigious mathematics journals in Europe, North America, Africa, and many other countries. He has further been an invited speaker at a number of international conferences and visiting researcher to such a very, very long list of institutions and countries that if I listed them, I fear I might be taking a substantial proportion of the allotted time for this inaugural talk. Ladies and gentlemen, I think it's now time for me to stop telling you about Professor Oluwatosin Mewomo, but rather to hand you over to this amazing mathematician. Over to you, Professor Mewomo. We look forward to your inaugural lecture and hearing more about the notions of amenability and Banach algebras and fixed point theory, the career in 2 paths. Over to you.
Thank you very much, Delia. The Deputy Vice Chancellor, College of Agriculture, Engineering and Science, UKZN, Professor Modi, the Dean, School of Mathematics, Statistics and Computer Science in UKZN, Professor Delia Knott, colleagues, collaborators, families, friends, and students. It is a great privilege to give this inaugural lecture on this Wednesday, 6th July 2022. I have the title of my lecture, and then you're going to see why I call it career in 2 parts. So the first part, which is the notion of amenability in Banach algebra, happened to be an area that I obtained my PhD, and the earliest part of my career, my research is majorly on that. In the last 8 years, I've tried to change to another aspect in functional analysis. So this will be the outline of my talk this afternoon. So I have a brief introduction. The second session talks about the first part of my career, which is the notion of amenability in Banach algebra. And the third session talks about what I've been doing the last 8 years with quite a number of my graduate students. About 50% of this slide this afternoon is to acknowledge family, friends, collaborators, hosts, and sponsors that are part of this success story that we are celebrating today. So I go to the background. So the lecture falls within the general area of pure and applied mathematics. My area of research, as I've said, is functional analysis, and that is the area that I've been working the last 20 years. The first part of my career starting with my graduate study master's at OAU, then at FUNAB, my PhD. So my graduate research work and earlier part of my career is in functional analysis, in particular Banach algebra. And the main focus in this research is the notion of amenability and its various manifestations. In this area, I have been able to graduate 3 doctoral students and 10 master's students. In the last 8 years, my research focus in functional analysis has shifted to fixed point theory with application to nonlinear and optimization problem. And also in this area, I've been able to graduate 11 doctoral students with 9 master's students. So this informed the choice of my inaugural lecture. And this lecture this afternoon, we cover these two areas of research. That is the notion of amenability in Banach algebra and their fixed point iterative problem. So in summary, in this lecture, I'm going to give a brief introduction and history to Banach algebra and the notion of amenability. It's good to know where this notion of amenability comes from and some of the experts that have worked in this area. In particular, I'm going to show how the notion of amenability started from major theoretical problem, and now this moved to abstract harmonic analysis and then to the theory of Banach algebra. Okay, I'm going to talk about various notions of amenability in Banach algebra and some characterization with some of my contributions in this area of research. And the second part of this lecture, we talk briefly on some notable fixed point iterative scheme in some important spaces with application. In particular, I'm going to show how iterative scheme can produce approximate solution to certain nonlinear problems or an optimization problem, and how to approximate the fixed point of non-linear mapping. Okay, so I want to go to the first part of my career, which is on Banach algebra and the notion of amenability being studied on Banach algebra. So when we talk about Banach algebra, we mean this A. So I mean A, which is always an algebra. Algebra means it is linear. Linear means if you pick two elements in that set A, the addition is there, it's close under addition, it's close under scalar multiplication, and product is also there. So this over the scalar field C in such a way that the product map is continuous. The product map is continuous. The Banach space in such a way that the product map is also continuous. So the product of two elements in the Banach space is there. The product can be defined in several ways. We have the pointwise product, composition of maps, convolution products. Every Banach algebra is a Banach space, but the converse is not true in general. So whatever you do in Banach algebra and Banach space can be done in Banach algebra. And the trivial case for Banach space with Banach algebra is when you take the product of two elements in the space to be zero, which is trivial in nature. Like the Banach space, Banach algebra was named after the Polish mathematician, which is Banach, Stefan Banach, who introduced the concept of Banach space, but Banach itself never studied Banach algebra. They are named after him simply because they are algebras that happen to be Banach space. As I've said, every Banach algebra is a Banach space. But the first to have explicitly named or defined Banach algebra with the name linear matrix rings seems to be the Japanese mathematician Nagumo in 1936. But the mathematician whose work really got the theory of Banach algebra on its way was Gelfand. I could remember when I started my graduate study at OAU then, my professor there happened to be an expert in Banach algebra. So my first lecture on Banach algebra, my first section on Banach algebra was taught by my supervisor, Professor Ushobi. Then we studied quite a number of works by this great mathematician Gelfand, especially his work on commutative Banach algebra, and that informs, arose my interest in Banach algebra. So Warren happened to be the one that came up with the name Banach algebra in 1945. I have the picture of Stefan Banach. So Stefan himself never studied Banach algebra. It was named after him just because it was an algebra that is also a Banach, is an algebra that is also a Banach space. So this is the man that his work actually, I've done quite a number of work at the early stage on Banach algebra. Gelfand, a lot of theories that he proposed for commutative Banach algebra. So I want to give some examples of Banach algebra before I move to the notion of amenability in Banach algebra. So I start with this semigroup. So when I say a semigroup, I mean a non-empty set, which is associative with an alternative binary operation. So that is called my semigroup. So when you have this semigroup X, now I want to take the collection of functions F that match the semigroup to the complex with the N1 norm. So when you take this collection of functions that might be semigroup to the complex with the N1 norm, with the N1 norm is a Banach space. Is that okay? So we want to make it a Banach algebra. Then we need to define a product. As I've said, every Banach algebra is a Banach space, but the converse is not true. So because the product of two elements in the Banach space is not generally in the Banach space, it's said to take the trivial product. So we want to try to define a product of this Banach space so that it can become a Banach algebra. So every function you pick in this space is of this form. It's of this form. And this condition is very, very necessary for the series to converge, where this is the Kronecker data. Okay, so if we pick two distinct points in the semi-group, the product of the canonical data on these two points is defined this way. Then we define what I call the convolution product on N1 of X. So this is the convolution product that is defined on N1 of X. When you take N1 of X together with the N1 norm, this convolution product is a unitary Banach algebra that is called the semi-group algebra. It's called the semi-group algebra. It is commutative only if the semi-group is an abelian semi-group. So that's an example of a Banach algebra that I've worked with over the years. Another example of Banach algebra that I've worked with is what I call the group algebra. The group algebra is defined on the locally compact group G. So to start with, we have a locally compact group, which is a group that is also a locally compact Abdel space, such that the product map and the inverse map are continuous at the same time. So when you have your locally compact group, you can always define a left-hand measure, which is me on your locally compact group. Okay, so N1 of G is now a Banach algebra, and this consists of measurable functions on this locally compact group G with the N1 norm. N1 of G, together with the norm, is a Banach space, and for this to be a Banach algebra, you must define the product. So the product is defined in terms of convolution of maps. So the product is defined, this is the product defined on 2 points, two elements to picking from N1 of G. So when you take N1 of G together with the N1 norm and this product, it becomes a Banach algebra that is called the group algebra. So the first class is what I call the semi-group algebra because it's defined on the semi-group, and this is a group algebra. So whatever you want to study on N1 of G, you have to study in relation to the group, the property of the group. So abstract harmonic analysis is just the study of this locally compact group G and the spaces and algebra that are associated with this group. So I'll give another class, which I call, these are called the operator algebras. So you have two Banach spaces E and F. We take B, E, F to denote the family of banded continuous linear operators. For linear mass, banded and continuity is just the same. So when your map is linear, linear map being continuous is the same thing as being bounded. So we take the collection of all bounded linear map from the Banach space E to F. Then we define the operator norm, which is defined this way. So we take the operator norm defined on it. So in a case in which our F is equals to E, so we call it BE. And when you take this space, the space of all bounded linear operator from the Banach space to itself, together with the N1 norm, which is defined this way, and this product, the product here is what we call the product by composition of maps. Pointwise product will not work here. So we take B of E, which is the space of four bounded linear operator from a Banach space E to another Banach space to a Banach space E with the operator norm and this convolution product, a composition of map product. Then it forms a Banach algebra that we call the operator algebras. It is unitary, but not commutative. The identity element in this Banach algebra is not the identity map. It's not commutative because this is not because of this composition of map is not commute in general. So because of that, it's a non-commutative Banach algebra. There are some nice close ideas of B of E that we have also worked with that are also Banach algebra. For example, we take the close idea of compact operators on the Banach space and the close idea of approximable operators on the Banach space. All these are Banach algebra that we have worked with. Then we go to the notion of amenability in Banach algebra. This started from a major theoretical problem. It actually started from the question posed by Hausdorff in 1914. And the question posed by Hausdorff is the following, that does there exist a finitely additive set function which is invariant under certain group action? That is the question that Hausdorff posed in 1914 with the help of his paradox. I'll tell you why we call it a paradox later, because mathematicians in these days believe that the result by Hausdorff and Tarski cannot be true because some laws of geometry are not actually obeyed. So that was why it was called a paradox. So with the help of a paradox, Hausdorff was able to answer the question in the negative. But a further investigation to the question by Hausdorff led Banach and Tarski with a paradox that now carries the name Banach-Tarski paradox. Now, the paradox is very funny in some sense. So this is a mathematical theorem that implies the following. So it implies that when you pick an orange, just a single orange, you can slice this orange into finitely many pieces. And you can take the pieces and form two oranges of the same size. So you start with a single orange, then you can slice this orange into finite number of pieces, and you can reassemble the pieces to form two oranges of the same size. This is an application of Banach-Tarski paradox. It was called a paradox because in his days, the mathematician in his days believed that this cannot be true. But I want to tell you that the Banach-Tarski paradox lies on two pillars. And one of the pillars is what my research in amenability is all about. The pillars are, number one, the axiom of choice. The proof of Banach-Tarski paradox rests on the following pillars. Number one is the axiom of choice. And number two, I'm more interested in the second pillar, which is the fact that the free group with two generators lack a property called amenability. So now, amenability started from the major theoretical problem. Now we're not talking about the amenability of a group, okay? So the concept of amenability originated from major theoretical problem by Banach and Tarski. It moves to abstract harmonic analysis where amenable locally compact groups were studied. So as at this point, what we know is when with a group is amenable, but we never know anything about the amenability of a Banach algebra. So when you have a locally compact group G, your locally compact group G is amenable if it possesses a left invariant mean. So that's what it means, meaning that you can always get a functional mean on the dual space of L1 of G, which is the Banach algebra L1 of G we're working with, that satisfies this condition. This shows that that mean is a mean, and this shows translation invariance. So now your locally compact group G is amenable if it has a left invariant mean, meaning that you can get a functional on the dual space of L1 of G that satisfies the first part of the condition, which shows that it's a mean, and the second part shows that it's translation invariant. Okay, so as a consequence of Banach-Tarski paradox, a free group being amenable is the same as not being paradoxical, meaning that your group is amenable if you cannot paradoxically decompose that group. Then we say the group is amenable. Okay, so as at this time, we only know when a group is amenable, but on Banach algebra, no information and nothing is being done as at this time. So if you want to get further details about what I've said, the brief historical background of some of these, you can look at some of this, my article that was published in 2021 by one of the SCBR journal. So, but in my research, I am primarily interested in the Banach algebraic aspect of amenability. What was studied to this point is the notion of amenability on a group, not on a Banach algebra, because a group on a Banach algebra are two different things on their own. Now, the groundwork for amenability in Banach algebra was laid by Barry Johnson in his classical memoir of the American Mathematical Society in 1972. And since then, this concept has occupied an important place in research in Banach algebra. So this is Barry Johnson. Barry Johnson is from the University of Newcastle in UK. And fortunately, my MSc supervisor, his own external examiner happened to be from the same university with Barry Johnson, and that is John Pin. Unfortunately, my supervisor for master's program had some co-author work with a colleague of Barry Johnson. Now, as I've said, before now, we know when our locally compact group G is amenable, but we don't know anything about L1 of G. G is a group, L1 of G is a Banach algebra. We know when G is amenable, meaning that G has a left invariant mean. For L1 of G, we don't know what it is to be amenable. So Johnson was trying to study the connection between the amenability of this locally compact group G and the Banach algebra defined on this locally compact group. And Johnson came out with this result. Johnson came out with this result that a locally compact group G is amenable as a group. Amenability as a group is not the same thing as amenability as a Banach algebra. So Johnson came up with this result that G as a locally compact group is amenable if and only if its group algebra L1 of G is amenable. Okay, so now if we take L1 of G to be an arbitrary Banach algebra, then we can now define what amenability is all about in terms of a Banach algebra, not in terms of a group. So in this case, when A is a Banach algebra, we say that A is amenable if every continuous derivation from A into the dual space of Banach by module X is inner. So this can also be defined in terms of cohomological group, which I don't want to go into that. So we can define this in terms of cohomological group, but this is just the literal simple definition that I can give by Johnson. Now, Johnson, we discovered over the year that the definition given by Johnson is too restrictive in the sense that it does not give room for stronger general theory that we will have loved to obtain. For this reason, over the years, myself and some other colleagues have been able to relax some of the constraints in the definition of amenability given by Johnson by doing the following. Number one, we try to restrict the class of Banach A module in question. So, for example, we have this notion of weak amenability coming from that. In such a case, you just replace this the dual space of S by the dual space of A itself. You have the notion of weak amenability. It's also possible to have a class of close ID of A. You can reduce this by a class of close ID of A, talking about idea amenability. You can also take this class to be the class of characters that are defined on A. So we'll be talking about the notions of character amenability. Another thing to do is that we can also relax the structure of the derivation themselves. Is that okay? Instead of saying that D is inner, we can say D is approximately inner. It's not inner in the real sense, it's approximately inner. So in this case, we'll be talking about the notion of approximate amenability, not the real amenability, it's an approximate amenability. Or in some sense, we can also combine restricting the structure of the bimodules. We can also relax have the approximate case of each of the classes of bimodule that we are taking. So by doing the above theory, various notions of amenability have been introduced in the recent year. Okay, now over the years, the definition given by Johnson is somehow restrictive and sometimes it's difficult for we to use to be able to find some interesting classes of Banach algebra that we would like to work with. So what we do is to try to find some ways of characterizing amenability. Without using the definition, how do we characterize amenability? So there are several characterizations in literature, but I just want to give two of such characterizations. So for me to give you two of such characterizations, I must be able to define what an approximate diagonal is all about and what a virtual diagonal is all about. So to define approximate diagonal, we must start with Banach algebra A. We start with Banach algebra A, and we take the projective tensor product of A by itself, which is this. Now, this projective tensor product of A by itself is a Banach A bimodule. When we define the left module version this way and we define the right module version this way. Okay, so we define an operator that is called a diagonal operator on its dual and its dual on the projective tensor product of A by itself to A, and it's defined this way, and the dual of the projective tensor product of A to the dual space of A. This is defined this. So both these two maps are A module homomorphism with respect to this module operation, both the left and right module operation that is defined above. So our Banach algebra A is said to have a bounded approximate identity. If we can get this net, if you can get this net from the projected tensor product of A by itself, such that this net satisfies this condition. So in that case, we'll be saying that A has a bounded approximate diagonal. So an element M in the bidual or the projected tensor product of A by itself is called a virtual diagonal if it satisfies this condition. So as I've said, the definition given by Johnson is too restrictive to be able to get nice class of Banach algebra that we love to work to show that it's amenable. So we try to characterize amenability in the following way, in forms of the virtual diagonal and approximate diagonal. So Johnson himself came with this result that the following are equivalent. Our Banach algebra is amenable using the definition that he defined that a Banach algebra is amenable if every continuous derivation from A to the dual space of the Banach bimodule S is inner. So using that definition, it is the same thing as saying that the Banach algebra has a bounded approximate diagonal. Another way of characterizing is to say that A has a virtual diagonal. So that means we can get this M for the dual space of the projective tensor product of A by itself that satisfies this condition, then it means that that A will definitely be amenable. Okay, so there are some useful relationships. You can study any of the notions of amenability on any of the classes of Banach algebra you want to study without looking at the structure in which the algebra sits on. For example, when you take the Banach algebra of bounded linear operator on a Banach space, whatever notions you want to study on B of X, you have to study in relation to the geometry of the Banach space. You have to study that with relation to the geometry of the Banach space. K of S, which is the idea of compact operators, and A of S, approximate operators, they are all Banach algebra. And whatever you want to study on these three classes of Banach algebra, you must be able to study in relation to the geometry of the Banach space, which is very, very important. We got on some nice result along the line, which may be for some of my work, I will tell you there are some geometric properties that are developed over the year, like property P lambda, property Q lambda, property A, and so on. So that if a Banach algebra, if a Banach space has some of those properties, and you define, you take B of S or A of S or K of S, you can easily show that some of them, we have some of these notions of amenability that have been discussed earlier. So structural application of amenability for semi-group algebra. This is semi-group algebra. For major algebra and for the group algebra are given below. Whenever the semi-group algebra is amenable, then the following must happen. The set of idempotent elements on that semi-group must be finite. Another thing is that S must be regular. Whatever you are studying, you cannot study any notion on N1 of X, which is a Banach algebra, without looking at the structure of the semi-group. So the structure of this semi-group or the behavior of this semi-group affects whatever you want to study on N1 of S. So whenever N1 of S is amenable, then the set of idempotent of this semi-group must be finite and S must be regular, and the semi-group must have an identity. For the group algebra, there's also some structural applications of the group algebra N1 of G or the major algebra being amenable. So for example, this is the result by Johnson itself, that the group algebra N1 of G is amenable as a Banach algebra if only if the group G is amenable. The major algebra N1 of G is amenable if only the group is discrete and the group is amenable at the same time. The N1 of G is approximately amenable if only if the G is amenable. So whatever you want to study on any of these classes of Banach algebra, you must study in relation with either the semi-group or the group or the Banach space that those Banach algebra are defined on. So I just mentioned some of my contributions on this area of research on the area of Banach algebra amenability. So these are some of the works that I've published over the years. And this is a paper published with one of my collaborators from the University of Victoria. And so this works on the character amenability of semi-group algebra. In this case, you work on N1 of X. So, and the class of Banach module that we define is the character that is defined on the Banach algebra itself. And this other one is work with one of my PhD students, is an student in this area of research that I graduated some years ago. This is an excellent work that I worked on several notions of amenability in Banach algebra that was published by Moiseevich in 2011. And this fourth one was the work that I worked on N1 of X. So in this case, my X is a semi-group algebra, and this work was done when I got the London Math Society Fellowship in 2007, and it was done when I was visiting at the University of Leeds in 2007. It was published by the Proceedings of the Academy of Science. Okay, so there are some other works that, these are some other works with some of my other students or collaborators. These are two of my collaborators from Iran, from Iran, yes, okay. So in this area of research, as I've said, I've graduated 3 PhD students and 10 MSc students. So that's from the first part of my career. So the second part is on fixed point problem. And this is what I've been working. It's also an area of functional analysis. That's the area that I've been working the last 8 years. So now we take S in this case to be either a Banach space or a Hilbert space. So S can be a Banach space, can be an Hilbert space. So we take C to be a non-empty closed correct subset of S, and we take this map. It's a non-linear map that maps this C to C. So we denote by f of t the set of fixed point of t. So that means the set of all points in this set C that this mapping T is mapped to the same point in X. So we call it f of T, which is the set of fixed point of T. So the fixed point problem is it's an interesting problem because of its numerous application, which you're going to see, if time permits, I'm going to give some application along in the talk. So the fixed point problem is formulated as follows. You want to find X in this C, such that T of X is equals to X. Okay, so the fixed point problem 3.1 has wide applications in differential and integral equation, machine learning, and so on. So in connection with fixed point problem are the following question. This is very, very important. I want you to pay attention to the problem. Number one, does a fixed point exist for this map? If you have your map, the map C to C, does this map as a fixed point? That's the starting point. That's the first question you must ask yourself. Now, if the answer to the first question is yes, the next question is it unique? Is it only one, or there are several of such fixed points? That is the next question. So the third question is, if the answer to the first one is yes, you can ask the second question. If the answer to the first question is no, there's no point asking the second and the third question. It doesn't make sense to ask about the second and the third question. But if this first question is yes, then you can ask the question for a second question, is the fixed point unique? If the answer to the first question is yes, you can go to the third question to ask, how can we approximate the fixed point? Because in the recent, you cannot find this fixed point analytically, fixed point of nonlinear map in an analytical way. You must have to approximate it. Is that okay? You must have to approximate. So my research in the last 6 years dwelt mostly on the third question, and which is the approximation of the fixed point of nonlinear maps. And the fortunate thing is that some of the optimization or the nonlinear problem that we see around, which I'm going to show you later, solving this optimization problem is also equivalent to solving approximately the fixed point of a suitable nonlinear map. So that is why this area of research is very, very of interest to me. Okay, so we have several classes of nonlinear maps that we have worked with, but I will just mention one of them, which is the non-expansive mapping. So if we take your Hilbert space H, and so you take your Hilbert space H, and you take the inner product defined on the Hilbert space and the norm. So your mapping T mapping to H is said to be L if she's continuous. If you can get this constant L greater than 0, such that this inequality holds. So in a case in which you take your L from this interval, this nonlinear map is called a contraction. In a case in which this L is equals to 1, then this nonlinear map is called a non-expansive map. And you can also define what we call the average map in such a way. So when you take alpha from this open interval 0, 1, and you can write your T as a linear combination of the identity map and another non-expansive map. In such a case, this T will be called an average map. Is that okay? So the remark we have there is that average map is nonlinear, is non-expansive. Any map of this form that you can write as a linear combination of an identity map and another non-expansive map is non-expansive. So the interesting thing is that the fixed point of this non-expansive map and the fixed point set of this average map, both of them are the same. And the last interesting thing is that T has a fixed point if you can get a particular S such that this trajectory is bounded, which is very, very important. Okay. So I want to give some early notable fixed point iterative scheme that have been used over the years. This is very, very known to quite a number of people. So we have the Picard iterative process. So we take S in this case to be a metric space, and we pick a starting point x1 in X, and we define xn plus 1 to be T of xn. So this is what we call the Picard iterative process. So the interesting result by Banach is the pivot to what we are doing. So Banach came up with this result in 2025 to say that if this Banach space S is complete, in the sense that every consequence we pick in it converts to a point in it, if this metric space is complete and this map T is a contraction, which I've earlier defined, then T will automatically have a unique fixed point. That's one. Not just having a unique fixed point, the Picard iterative process converges to this unique fixed point. The Picard iterative process converges to this unique fixed point. But the interesting thing is that for more general map than the contraction, because the map T here is a contraction, the Banach contraction mapping principle will not be applicable. So because of that, we have to look for more iterative process that generalizes the Picard iterative process. One of such is what we have, the Mann iterative process. So this is defined on Hilbert space. So we have your starting, you pick a point x1 from H, and you define Sn plus 1 as you have in 3.3. Okay. So one interesting thing is that this Mann iterative process only converges weakly. And we want it to converge in a strong sense. So this only gives a weak convergence. In 2007, Agawa also introduced another class of another iterative process called the S-iterative process. So in this case, you take S1 for the starting point, you define Xn plus 1 and Yn. So one interesting thing is that the S-iterative process is independent of the Mann iterative process, but it has a better rate of convergence, because we want to, sometimes when you finish your work, you want to compare your iterative process with others in terms of the rate of convergence, that yours perform better in terms of CPU time and in terms of the number of iterations involved before convergence is achieved. So we realize that the Picard, the Mann, and the Ishikawa and the S-iteration process only converges weakly. So for finite dimensional space, we don't have a problem with that, because for finite dimensional space, both the weak and strong convergence coincide, they are the same. But this is not true in an infinite dimensional space. No, it's not true in finite dimensional space. And most of the real-life problem we want to solve, we can find them in an infinite dimensional space. And none of these iterative processes that I've discussed earlier gives a strong convergence. So because of this, EPAM introduced an iterative process which converge strongly to a non-expansive, to the fixed point of a non-expansive map. And this is the EPAM iterative process. So you fix U from H, your Hilbert space H, then you start with X1, which is the starting point, and you define Sn plus 1 to be as defined as 3.5, where the sequential is coming from the open interval 0, 1 in this case. Okay, so another way to generalize this A-prime type, so A-prime iterative process gives a strong convergence, which is more desirable. But if you replace this U in the A-prime iterative process with f of xn, if you replace U with f of xn, then you will have a generalization of that A-prime iterative process, which is called the viscosity iterative process, which is this. So it's the same thing with EPAM. The only difference is that you replace your U with f of xn, where this f is a contraction on the Banach space, on the Hilbert space. Either Hilbert space or Banach space is fine. The good result here is that the viscosity iterative process has a higher rate of convergence than the EPAM iterative process. Though both of them converge strongly, but one performs better than the other. So over the years, there have been several iterative processes that have been developed as a modification of the ones that I have introduced earlier, and these have been used to approximate the fixed point of nonlinear maps, optimization problem in Hilbert, Banach, and other spaces. For example, we work in Hilbert space, Banach space, and Adama space, which is a complete cat-zero space. Okay, so some of the optimization problems that fixed point iterative method have been useful are the minimization problem, the variational inequality problem, equilibrium problem, and so on. And all this has a lot of application in economics, in computer science, in engineering. If time permits, I'm going to give an application to computer science and find application also in machine learning. Is that okay? So many problems arising from all these fields above can be modeled as an optimization problem. And one of the most successful methods for solving this optimization problem is the fixed point method. Is that okay? So as a result of this, a lot of research effort have been devoted in the recent time to develop iterative method for approximating the solution of this optimization problem. In general, finding a solution of an optimization problem is equivalent, that is the key thing, is equivalent to finding a fixed point of a suitable nonlinear map. Okay, so I will give some of the optimization problems that we have worked with over years, and then I will give an application with some of our results. Okay, so we have what we call the variational inequality problem. These are a lot of work have been done on variational inequality problem. So in this case, you can work on Hilbert space, you can also work on Banach space. So either E can be Hilbert, it can also be Banach, is fine. But C is a closed convex subset of either the Hilbert space or the Banach space. And so the variational inequality problem is the problem of finding a point X star in this C such that this equation 3.70 and A is a nonlinear map from either the Banach space or the Hilbert space to the dual space of the Banach space. Okay, so it is known that solving this variational inequality problem 3.7 is equivalent to solving the fixed point problem 3.8. So that's why I said solving optimization problem using fixed point iterative method is equivalent to solving a fixed point problem. So the solution to this 3.7 is equivalent to the fixed point of this map. So you take the composition of the project, the metric projection, and compose it with I identity mapping on gamma. Gamma is just a number greater than 0 on A. Why this A is the cost operator in the variational inequality problem. So the solution to this 3.7 is equivalent to the fixed point problem that we have in 3.8. And there will be a lot of fixed point iterative methods that have been developed to solve this problem in the recent year. So another generalization of this variational inequality problem is the equilibrium problem. So equilibrium problem is you are finding a point. You can also do the same problem on either the Hilbert space or on the Banach space. So either on the Hilbert space or Banach space, C is always a closed, non-empty closed convex subset of either the Hilbert space or the Banach space. Why this F is a bifunction. So the equilibrium problem generalizes the variational inequality problem, and this is a problem of finding the point X in C such that F of X, Y is greater or equal to 0 for every Y you pick in C. And this F is a bifunction. Is that okay? So if it's the only solution of this solution set of this equilibrium problem by EPCF, then this result shows that solving this equilibrium problem 3.9 is also equivalent to finding approximately the fixed point of a suitable nonlinear map. Okay, so look at this lemma. So we have a bifunction with some assumption. Yeah, I don't want to put the assumption there because of time. So look at this map, the map TR of F, it's a resolvent map operator. So from H, the Hilbert space to C, and it's defined this way. Now look at this result. This set is not empty. Is that okay? It's not empty, and this map is single value. So the key result here is that the fixed point of this resolvent operator, the fixed point of this resolvent operator is the same thing as the solution of this equilibrium problem 3.9. So solving this solution finding the solution of this equilibrium problem 3.9 is the same thing as finding the fixed point of this resolvent operator. So you can see why fixed point iterative problem, iterative method is very, very useful. So another useful result or problem we have worked on is called the split feasibility problem. I'm going to skip because of time. I want to go to a point in which I give some application. So we have the zero, the sum find approximately solution of 0 or 2 maximum monotone operators. So we have monotone operators A defined from the Hilbert space to the set of power point, the set of the power set of H. So it's called a monotone operator. If you pick 2 elements from the Hilbert space and you pick U from A of X, because A of X will be a subset of H and A of Y will be a subset of H. So we pick 2 points for this set and this inequality holds. So we consider the problem of finding a 0 or sum of 2 maximum monotone operators, which is A and B. And the problem is solved about you want to find S in H, so that 0, so that X is in the 0 of the sum of these 2 maximum monotone operators. Okay, so we denote the solutions, the solution set of this sum of monotone operators on either Hilbert or Banach space by A plus B inverse 0, and which we know it is close and convex, which is very, very important. If it is not close and convex, we run into a problem. So we assume it's not empty. This is very important, and we define the resolvent operator as J lambda V. And the interesting result is that the fixed point, if S is in the fixed point of this computation of this resolvent operator, or the second one, then X will solve the inclusion problem that we have in 3.12. So S is a solution of the S is a solution is in the fixed point of this resolvent operator or the second one, if and only if W, you take the resolvent operator on that X to be a solution of the monotone inclusion problem that we have in 3.2. So this operator, the resolvent operator is what we call the Peaceman and Ransford mapping, which is in general not average in general, though it's non-expansive. And the second one is what we call the Douglas Ransford operator, which is half average. So if we use the first resolvent operator to approximate the solution of the maximum monotone operator, you will discover that it fails to converge in the real sense. But when you use the second resolvent operator, which is the Douglas Ransford operator, then if you use it to approximate the solutions of that monotone inclusion problem, you are going to get a weak convergence for that particular problem. So this is a generalization of that of these two operators. So I want to go to the recent development in this area of work. In the recent time, several authors have studied the above iterative process that I've mentioned, either the PCAT or their modification to approximate the fixed point of nonlinear maps and the solution of an optimization problem. So what I'm going to do in the last part of this talk is to give one of our results. In this case, we want to approximate the solution of this generalized split infinity problem using the fixed point iterative method, and also to give an application to show you that this has a lot of application to image restoration and sigma processing. I hope time will permit me to give the application. So we define what we call the generalized split feasibility problem for a class of monotone inclusion problem is for you to find X in the Hilbert space H1. In this case, we have two Hilbert spaces, H1 and H2. You want to find S in the Hilbert space H1 such that that X is the zero of the sum of two maximum monotone operator A and B, and the fixed point of the fixed point of T of S is the fixed point of a non-expansive map J that map H2 to H2. Okay. So we have some assumptions because we need to impose some assumptions and restriction before you can be able to obtain your strong or weak convergence result. So we have some assumptions. The first assumption is that solution space of the problem is non-empty. That is very, very important. And we put some constraints on our control parameters, which are these. So theta n is in 0, 1, and the limit of theta n as n goes to infinity is 0, and the sum of the series is that. So, and let's look at what our algorithm is all about. The algorithm we propose in this case is the following. So number one is to have the initialization. We take gamma and lambda to be greater than 0, mean, and mean to be from the open interval 0, 1, and gamma alpha greater equals to 3. So we pick two starting points, X0 and X1 in H. There are two Hilbert spaces, H1 and H2. So we have the first step. The first step here is all about we try to find this gamma alpha n that we are going to use in the natural term of the algorithm. So the next step is the natural term of the algorithm. So this is the natural term. The essence of this natural term is step 2 is to speed up the rate of our convergence of our iterative method. So each of the time we use the natural time, the essence is that we want to speed up the rate of convergence. So we go to the third step. So we compute our xn plus 1, and this is just a modified Mann iterative method. And so we have the stopping criteria. So the stopping criteria is that whenever yn is equals to un equals to wn and xn, then we stop. Otherwise, we start the process again. We take n to be n plus 1, and we go back to step 1. Okay, so here we use what we call the step adaptive set size. Self-adaptive set size. I don't want to go to reasons why we use that. This is very, very important. It has a lot of implication in our computational results. So we use two step adaptive set size, gamma n and lambda n. And these are the results that we obtain. Number one, suppose yn equals to un equals to wn and xn as defined above, the xn must be in the solution space. The solution space is gamma. And the next result is to say that the sequence generated by our iterative method is bounded. Very, very important to show it's bounded. And the theorem, the main result is that this sequence xn with some assumptions, which I don't want to mention here, converges strongly to the solution of this generalized feasibility problem. And the interesting part is that the solution we obtain is a minimal solution of that particular problem, which is an interesting result. Okay, so the last part of this talk is just to give an application, and we have 2 applications, but I'll just give one because of time. So we try to apply our result to what I call the image restoration problem. This can be formulated as V is equal to D of S plus E, where this S in Rn is the original image you are starting from. You start from this original image, and you have what to call the blurring matrix. And V is the observed image, while E is the Gaussian noise. Okay, so we have the original image X, and we try to deform its sense, and we want to use our algorithm to restore that particular image to the original form. I want to see how close is the restored image to the original one. So problem 3.9 is equivalent to this minimization problem that we have in 3.20. Okay, so using our iterative method, we try to look for 2 images. Number 1, we consider the cameraman image, which is 256 by 256 cameraman image, and the second image that we use is 120 by 128 medical resonance image. And we use a toolbox from our MATLAB toolbox to be able to see how we can use our iterative method that we discussed earlier to be able to restore that particular image, and we want to see how close is the restored image to the original one. We measure the quality of the restored image using what we call the signal to noise ratio, and this is defined this is defined as 20, this is defined thus, and the higher or the higher the signal to noise ratio, the better the performance of the iterative method. Okay, so here we have our numerical, our results. So there are 2 images that we try to work with. Number 1 is the cameraman. So this is the original image. This is the original image. This is the blur image. Is that okay? This is the image that is deformed using the blur matrix D. And so there are 3 algorithms. 3.2 is our own algorithm. This is our own algorithm 3.2, and there are 2 algorithms that we are trying to compare our results with to see whether our result performs better than those 2 other algorithms. So you see from the next table to show that our algorithm performs better than the other one. It says that the signal to noise ratio for our algorithm for restoring this image back to the original form is higher than the other 2 algorithms that we have compared with. So another image that we work with is what we call the MRI image. So we have the original image. This is the deformed or the blurred image. So we use our algorithm 3.0, our algorithm that I've discussed earlier, to restore this image, and this is what we got. So we want to see how close is our restored image to the original one, and we compare our restored image with 2 of the existing results. And the numerical table, the table we got here shows that you can see the time of CPU time, ours perform better because the CPU time of ours is lower than the other 2 that we compare with. And you can see the signal to noise ratio that ours is high, showing that our algorithm restore the image better than the other 2 algorithms that we compare with. Another application that I would like to talk about is we also apply our algorithm to what we call the sigma processing problem, which is similar. It's the same equation that we solved for the image restoration problem. It's the same V plus D is S plus E. So the process is similar to the one of image restoration. So not to waste time, I think my time is almost up. So I will just mention some of our contributions in this area of our second area of my research, which is a fixed point iterative problem with application to non-linear optimization problem. And we are able to publish over 100 articles in this area of research in the last 5 years. And in this area of research, I've been able to graduate 11 graduate students with 9 master's students, and 5 are currently working on this area of research. Several articles have been published in this area of research in the last 8 years. Some of the articles are listed here. Some of the articles are listed here. I cannot round up this talk this afternoon without expressing my sincere thanks and appreciation to all. There are too numerous for me to mention who have contributed and supported me one way or the other to this level of my career. I will always say that these are part of the success story that is being celebrated today. The foremost person that I want to appreciate is God, because there's nothing I am today that I am by myself. I want to thank God for the grace, for the strength, for the wisdom, for the support that He has granted unto me to this day in the journey of my career. I will always say that I owe a lot to Jesus, and to God be the glory. I want to thank my family. I thank my parents, my late dad, Mr. Oluwatosin Mewomo, and my mom. We stay alive today. Mrs. Dr. Mewomo. I want to thank my healers, who are the Ayola families. I want to thank my darling wife and my loving daughter, my wife, Dr. Mudupe Cecilia Mewomo, and my daughters, Oluwadarasimi, Oluwadosa, Oluwadabira. I want to thank my sibling, my late brother, Babatunde, and my 3 other siblings, Shegundoyin and Akin. I want to thank the Mewomo families. I want to thank the Laronsi families. I want to thank the Ayola families. I want to thank the Akrinola family. I want to thank my advisor, my professor at my master's level, Professor E.O. Shobi, is late now, who introduced me to the notion of amenability, who introduced me to the notion of, who introduced me to Banach algebra theory. I want to thank my PhD supervisor, Professor J. Ogutuashe. I want to thank my mentors, my undergraduate teachers, Professor Yati Sholari, Professor Ogutuashe, Professor Bola, Professor Denir, and so on. And I want to thank Professor Gades. My connection to South Africa is due to Professor Gades. He's been a real mentor in the history of my career. I thank him for hosting me, I think twice in Leeds. They got the London Math Society's King Fellowship for me to visit 3 universities in the UK in 2007 and in 2010. I want to thank you for the excellent time that we have had together. I want to thank Professor Vokarondi from University of Alberta, Canada, John Willis from Newcastle for all their contribution and mentoring over the years. I want to thank my graduate student and my postdoc. I want to thank my overgraduate students. I want to thank my doctoral student that I graduated today. The names are there. They have done well. They are really part of this success story that is being celebrated today. There's nothing I would have been able to do without the support and the encouragement and the contribution of these wonderful and excellent students. I want to thank my current students, 5 of them. They are also there, my postdoc fellow. I want to thank their contribution. I want to thank my colleagues from FUNAP. This is where I got my first degree, and this is where I worked as a staff for about 13 years before joining UKZN in 2015. I want to thank the School of Maths. I want to thank the university for providing an enabling environment for me to be able to achieve this level of feat in the history of my career. In particular, I want to thank Professor Sagi for his numerous contributions. A good number of the code at the early stage of my career in fixed point theory was supported by him. He has really been a sort of help to me in this area. So I want to especially thank him. My collaborators over the last 8 years. I want to thank Professor Gibali from Israel. I want to thank Professor Kamsi from USA. I want to thank Professor Abbas from Lahore. I want to thank Professor Yekini from China, Dr. Khan Sevikan from Qatar. I want to thank Professor Jensen Yao from China, Professor Jensen Shou from Korea. I want to thank Professor Prasit from Thailand. I want to thank Don Kwali from China. I want to thank Professor Abbaset Bodagi from Iran. I want to thank Fasid from Iran. I want to thank my good friend from the University of Victoria and my wonderful collaborator, Dr. Shas Mepa. I want to thank Dr. G.C. Gunadi for his contribution in this area of research too. I also want to thank my numerous hosts during my visit to several research institutions, Professor Ariel Blanco from Queen University, Belfast, Dr. Sandra Port and Professor Ken Brown from University of Glasgow, UK. I want to thank Professor Gades from University of Leeds, Professor Barry Gray from ACE, who hosted me 2 months in ACE in 2013. I want to thank Professor Taylor Kett from University of Dallas in Canada. I want to thank Professor Young Chan from University of Manitoba in Canada for hosting me some years back. Dr. Shas Mepa hosting me in University of Victoria twice or 3 times in UP. I want to thank my founder, the founder of my research and my graduate student to date. I want to thank the London Mathematical Society for the Skinford Fellowship and the travel grant that I've enjoyed from them, the International Center for Logical Physics in Italy and Simpa, France for the 2-month visit to WAT and my visit to ICTP some years back. I want to thank IMU, who funded 2 of my graduate students. One of them has graduated now, and the second one is currently on his PhD work. I want to thank COE Mass, who funded 8 of my PhD students and 1 postdoc. I want to thank UKZN and NRF for funding 2 of my PhD and 2 of my postdoc. I want to thank AIM South Africa for funding 2 of my MSc students. And I want to thank Professor Mewomo from Technion University in Israel, who is currently hosting 3 of my SPhD students as postdoc. I want to thank my pastors and brethren, for example, National Overseer, the Bank Life Ministry, South Africa. I want to thank my state, my professional pastor, Pastor Mike Odusoya. I want to thank my national coordinator, DSCF in South Africa. I want to thank Professor and Pastor Oyediro and Olaleru from University of Lagos. I want to thank my state DSCF coordinator in Nigeria and the current state DSCF coordinator, Pastor Moiseevich and Adiju Igbe, Daniel and Omutoke, Popola, and the DLBC and DSCF family from Abeokuta, Nigeria, Pastor Rechid, National Overseer. Each time I visit National Overseer, each time I visit Canada, the National Overseer will always make a very conducive environment for me to relate and relate. And that's a nice time with the brethren in Canada from Manitoba, from Toronto, and from Halifax. So I want to thank Pastor Rechid, National Overseer of the DLBC Canada for all the nice time that I've had with him and the brethren in Canada. I want to thank Dr. Deji Akinnuola, who hosted me and accommodated me for some time when I visited Toronto in 2017, I think. I want to thank Pastor Samuel Paul, Professor Daniel, Pastor Shegun Adeniran, Adetorige, who hosted me and they took good care of me when I visited Winnipeg some years back. I want to thank Pastor Sunday Olaleye and the Olu brethren for their hospitality and fellowship when I visited Finland some years back. And Pastor La, when I visited Halifax in Canada for the love and care. Many friends, too numerous to mention, that have contributed to the history, to my career, to my employer, FUNAP, that I spent 13 years. I thank you for the good works that you have done. I want to thank UKZN for providing an enable environment for me to strive and achieve this level of success. Thank you very much for the time. I want to say our journey still continue. Thank you for listening and God bless.
Thank you so very much, Professor Mewomo. Yes, I want to thank the more than 200 people who listened to you from the beginning to the end. And I'm sure there are many hundreds who are also watching as you were telling us about the paradox and amenability. It's amazing that you believe that the two are opposite, and the mathematician tells you that basic mathematics is applied. I do want to emphasize the fact that your presentation shows that UKZN is an institution of choice. It attracts and retains academic and support staff of the highest caliber by creating an intellectual environment that fosters and stimulates academic life, and a climate of organizational citizenship in which all staff recognize and understand their role in ensuring the success of this university. Congratulations on reaching this significant milestone of your life after choosing UKZN. Therefore, I thank you for choosing UKZN. Thank you also to everyone who contributed to your growth and development as mentors, collaborators, and partners. Thank you to your students who added value to your growth as you were developing them. The university also expresses the highest gratitude to your family who provide support to you while they generously share this wonderful asset with us. Long live to you as you continue your career at UKZN. Thank you so very much, everyone.